Okay, so there are two forces acting on the car. There's the forward propelling force F, which is constant, and there's the backward drag force, which is proportional to the speed. So let me write it as K times V. So V is the speed. So at first, the car is going to accelerate because there's a net force in the rightward direction, and therefore the car will pick up speed. But as the car picks up speed, the drag force is going to increase because it's proportional to V, you see. So as the drag force increases, the net force becomes ever smaller. And it becomes smaller and smaller, the net force becomes smaller and smaller, and therefore the acceleration also becomes smaller and smaller. That's why the rates of increase of the velocity will become smaller and smaller, until when you're traveling at the speed that's so fast that the drag force is equal to the propelling force. That's the so-called terminal velocity, and your velocity will stop increasing there. So what I've just sketched is the velocity time graph. The acceleration time graph is even more obvious, right? Because we start off from a net force of F, and the net force becomes ever smaller and smaller and smaller because the drag force becomes larger and larger. So with a smaller and smaller net force, the acceleration also becomes smaller and smaller. Net acceleration is just net force divided by the mass, right, of the car, which is a constant. Now, this acceleration is supposed to approach zero asymptotically. Just like the velocity is going to approach the terminal velocity asymptotically. So it's not going to be a straight line graph that hits zero. Why that so? Two ways to convince you. One is theoretically the acceleration will never reach zero. The next thing I would say is just, well, it is through mathematics. We know that this is going to be an exponential graph and not a straight line graph. So it's all in the mathematics.